same thing that's actually happening itself. Okay, so that's my little rant. So let's just go over surface integrals. Okay. Now notice we have the same picture as surface area. All right, and I told you guys surface area will do the same thing. We're going to get a red vector here on the parallelogram, and there's some involved. That's my surface area. So what in the world is a surface integral, or what's the difference in it? Okay. Now this is a very interesting, again, abstract concept. Now, let's suppose we have this surface in 3 dimensions. Okay. And let's suppose we have a cloud over it. We have a little cloud. You know, everybody's seen a cloud before. Okay. Now this is in a higher dimension, right? This is 1, 2, and 3, and something above it. So this is like in 4 dimensions. I know, very abstract. Just bear with me. Okay, so it's 1 dimension higher. Okay, now what we want to do is we want to find the area underneath this cloud that touches the surface. So kind of like this stuff right here. Okay. Now, when I say area, right, I would say that in air quotes. So the area, because essentially that's the volume, right? Because now we're in 3 dimensions, so we have surface, right? So, but the easiest way is, look, you know, if I look down on the cloud, I see that area between it, like the integral between it, and then we just go over it. So it gives it the volume of the entire portion of it. Okay, that's technically what the surface integral actually is. Okay, because this surface is between x, y, z, hence the reason why it's 1 dimension higher. Now, if I look down on this cloud, we get a 3-dimensional object. Hence the reason why it's just an x, y, z. But again, it's very theoretical because of that. Okay. So again, the whole point of a surface integral is I want to find the surface or the area between this cloud, which we're going to be actually dealing with our function or vector function, more importantly. So below this vector function, vector field of this function, and in between another surface. That's what a surface integral actually becomes. So it's very similar to a surface area on that aspect, because if this function here is exactly on the actual surface, we get surface integral. So a lot of times in your textbook, and a lot of people that explain it say that surface area is a special case of a surface integral, because once I just bump it up a little bit, then we get a surface integral, because that distance now becomes not 0, it's actually more. Right? Again, very theoretical, and I'm explaining, but that's, I think, the best way I can tell you how a surface integral represents itself is, again, if you're looking down on objects, you see this cloud, you want to see the buffer between that cloud and the surface. Okay. Again, very theoretical. I totally understand. Okay. But that's what we're going to be about to do now. Okay. Now, the good thing is, like I said, the surface area is a special case of it. So if you notice, these equations are pretty much identically the same with just one little tweak, right? The only tweak is last time we did not have z because we were only in 2 dimensions. This time, because it's a 3 dimensions, we have x, y, and z, except we go from a 2-dimensional object, which is nice, right? We're integrating with respect to just a region in both cases. What that means is the the z term here is going to be in terms of u of v if it's parameterized, or x and y if it's just in terms of x and y. Okay? So we just have one extra term above it, right? So think of it as a higher dimensional surface area. That's easier to explain what a surface integral represents. Okay? But unfortunately, it gets a little harder. And again, okay, if surface integrals are hard to integrate, what's an easier way to do it? That goes into the next section when we talk about Stokes Theorem. It makes the integration a little easier to deal with, okay, as you'll see right now. So here's our 2 types of ways to find surface integrals. So again, if we parameterize it with r, this is going to be our equation. And if we parameterize it with just x and y, this is going to be our equation right there. Okay. So let's find out how difficult, just a straightforward integration is going to be before we get a little bit of help using Stokes Theorem. So we want to compute the surface integral of x squared ds where S is the unit of sphere, x squared plus y squared plus z squared equals 1. Okay. All right. So according to our equation, it's going to equal to, oh yeah. So we can either two different ways. We can use parameterizations or straight respect x and y. Now I told you guys a hint last time that the only way we could do x and y is, or the trivial one, is if one of these is already, you could solve for one of these without being squared, right? Like plus or minus, which we can't because it's a sphere. So therefore we can't really, nicely solve for a variable without having a square root in it. So that means we have to parameterize it. Okay. So in other words, find R in this case, right? With respect to two different variables like u and v. Okay. Now, since we have x squared plus y squared plus z squared, the easiest one to deal with is our, well, not the easiest because everybody hates this one, but the most popular one is going to be our sphere, right? So a sphere represents its rho, phi, and theta, everybody's favorite, right? Itself. Yeah, yes, I know. Now the good news is rho is just going to be 1, right? So it's going to be rho squared equals 1, so rho is going to equal 1 in our case. Okay. So when we do our conversion, it's just going to be 1 times sine phi cosine theta. X or y is going to be 1 sine phi sine cosine, and then z is equal to 1 times cosine phi, right? So now notice this is now just in terms of two variables, which is what we want. Okay. So now the next step we do, since we have that, is our transformation. So we know, so this is basically our vector r here with respect to rho and theta, right? X, y, and z. So the next thing we got to figure out is we have to find the partial derivatives with respect to both the variables. So in this case, u and v will be our respective theta and phi. Okay. All right. Now, we actually did this earlier, last section, so I'm just going to skip that because of time itself. And we found out that this length here is just equal to sine phi. Well, it was actually equal to 25, right? Sine phi, but our radius is 1, so it's just going to be 1 of it. Everybody remember that? You did it yesterday. If you just go back on the notes. No one's asking, saying anything, but I'm still assuming everybody got that. Very good. Good. Okay, so I can skip that. Yeah. So I just for space because that take all the portion, right? The cross product was painful yesterday. Okay, so we did that earlier. Okay. Now we also got to convert our function, right? So x squared is equal to sine squared, right? Just looking at this, sine squared phi cosine squared theta. And so we got that down, right? So now when we do our double integral, now the good thing is because we have a sphere, theta goes from 0 to 2 pi, because it just goes around the entire sphere. And phi goes again from 0 to pi, right? The boundaries of themselves. And we have no rho because it's only in terms of two variables, right? So we plug this in, so we sine squared phi cosine squared theta phi d theta. And then, oh, almost forgot, because we converted to spherical, you have to multiply it by its also respective one. So which is phi squared, which is just 1 sine of phi. So this is going to be phi to the third power there. Okay. All right. All right. Now, so there was a nice little theorem that said if we're multiplying, we could separate the partial derivatives or partial integration and do them individually. Only if we're multiplying, right? Add and subtract doesn't help because it's combined. And these are not in terms of anything, just they're strictly numbers, which is nice. So what I mean by that is we could do this individually. So just the cosine or just the theta of everything, we're going to multiply by the other part. Or in other words, just the phi stuff. So we do one each individual. It's just easier to look at, right? Itself. And trust me, when you do this one, it's just easier to look one individually than the other. Right? Okay. So this one right here, we know how to do, right? It's the same thing as when it was sine squared. The only difference is it's going to be plus 1/4 instead of minus 1/4. So that integral is actually the same. So this is the same thing as sine squared. The only difference is this becomes a plus instead of a minus 1/4. It's literally the same, which is kind of funny. And so that property still holds there. Okay. Now, on this side, however, a little note. So I'm not expecting you to remember this. This is not going to be very good. I'm going to pencil work with it. So quick little note. Okay. In order to integrate sines of higher power, you want to break them up into just sine squared theta times sine theta, and then use the Pythagorean identity, right? So sine squared is the same thing as saying 1 minus cosine squared theta, and you just distribute this, so you get sine theta minus cosine squared sine theta, like that. Okay. So what that does is now we just integrate each one individually. So remember, this is being multiplied. So here, the integral of sine is negative cosine. And here you just use a quick u substitution, right? Let u equal cosine theta. So then du is equal to negative sine, all that fun stuff. So this becomes positive 1/3 cosine cubed theta. Hopefully you guys recognize that, right? We've been doing that a lot this semester, right? This conversion, this u substitution. Everybody good? Or you guys want me to show you the next steps to get there? Everybody good? Assuming that's a yes. Oh yeah, that's fine. Thank you. Yeah, thank you. Oh yeah, so these are all 5. Good catch. There you go. Good. Okay. All right. So now we just plug it in, right? Which is the best part. Okay. So let's see what we get here. So plug in 2 pi everywhere. This just means pi. And this is gone, right? So it's just going to be 0. And then so minus. And then we plug in 0. And this all goes away, right? Even the sign goes away. So this part just ends up being pi on that side. And then we're going to multiply by the same thing. So we're going to plug in pi for cosine. So this we got to be careful with your negatives, right? I saw a lot of this in the test. Cosine of pi is -1. -1 times negative gives you a +1. Okay. Plug it in, same thing, right? This gives you -1. -1 to the 3rd power is a negative. So this is -1/3. So the first part's going to be 1 minus 1/3. Okay, minus, now we just plug in 0. So cosine of 0 is 1 with a -1. Cosine of 0 is 1, so +1/3. Okay. All right, so this is going to be pi on the outside times what? So if I distribute this negative, this now becomes a +1. and this becomes a negative 1/3, right? It's just distributing. And notice we get positive 1 plus positive 1s, which is 2, minus 2/3. Right, just easier to look at. And then putting this together, right, just giving common denominators, so multiply this by 3. So that's going to be 6. 6 minus 2 is 4 over 3, and times the pi. And there we go. So if you notice, this is a very long question because even though we just skipped, well, we only skip up, we did this earlier already. So imagine having to do this also, right? So these questions get very lengthy. Hence, the next section will help us out, right? We have to do this the hard way, and eventually someone who's smart finds out an easier way, right? Just like everything else in math. So again, this is difficult because we got to do everything in spherical, right? So that's what's so hard about it. Now, let's suppose, well, what if we have a surface integral where we can actually use x, y, and z, right? Sometimes it's harder, sometimes we have to convert to polar, but don't worry, this one actually we don't really have to. This one's a straightforward one. Okay? So let's compute the surface integral of y ds, where s is the surface of z equaling, all right, perfect, z equaling 2x plus 3y squared with x. So even gives us the boundaries, which is easy and nice, right? They give us boundaries between x and y respectively. Okay, so for this one, we're going to use this equation right there. So we want everything in terms of just x and y, which check. So that's the g term. So this is going to be our g here. And therefore, now we're just take the partial derivative of the z term, which is just this, with respect to x and y, and plug them in, and don't forget to add 1 inside the square root. And hopefully we don't have to convert to polar and all that fun stuff. You know, who knows, right? Itself. So we'll just start doing that. So let's find zx. So that's the partial derivative with respect to x, just going to be 2. And then zy. So this is going to be partial derivative with respect to y, which is going to be 3 times 2 is 6y. Okay, so now according to our equation, this function here has to be in terms of only x and y, which check, it just has a y, which is even better, right? So this is going to be the double integral, and I'll do y first. Yeah, I'll do y first. So it'll be from 0 to 1, 0 to 2 of y times the square root of each 1 squared plus 1. So 2 squared plus 6y squared plus 1 dy dx. So this gives us, that's 4 plus 1 is 5 plus 36y squared. So far, so good. And now notice this is actually really nice because we don't have to convert polar because we have that y on the outside, right? We go straight to u substitution. So then du is going to be 3 times 36, so 72 y dy. So divide everything by 1 over 72. And look at that, beautifully, right? Oh, maybe be consistent because we're just doing y first. So therefore, it's going to be 1 over 72, the integral of just u to the 1/2 du, and that gives us u to the 3/2 with a 2/3 here. Right. So it's going to be 1 over 72 times 2/3, where u was 5 plus 36y squared with a 3/2. Evaluated at 0 and 2. Okay. All right. So I'll bring this on the outside. So 2 is 36, and then 36 times 3 is what, 70 something? 79. Oh, way off, 108. So 1 over 108. And this is evaluated as 5. That. Okay. Up here. Okay, let's see what we get. Believe it or not, this is actually the whole problem right here. Okay. So if I plug in 2, I get 2 to the fourth is 2 squared is 4. And then 4 times 36 is 144 plus 5. This is 149. So this is going to be 149 to the 3/2. Minus, when I plug in 0, this all goes away. So I need to skip 5 to the 3/2. All right, let's see what we get. So 149 raised to the 3/2 power. And then minusing 5 raised to the 3/2 power. And since I'm at it, I'll just divide by 108. So I get approximately 16.74. All right, now, unfortunately, we're not done, but we're pretty much done. Because now all I have to do is integrate this with respect to x. And the good thing is there's no x. So it's just going to be 1674 because it's evaluated from 0 to 1. So there we go. So like I said, a little easier example than the one above. Questions here at all? Good. No questions? Okay. All right, good. No questions then. All right. So let's keep going on this surface integral. So I gave you kind of a definition of what it is. Hopefully this is a little bit better explanation, or you get to understand this more with the next page here. All right. So why is this interesting, or why is it interesting at all? Right? Besides the concepts that S applies. So theoretically, because I'm a very theoretical person when it comes to for my mathematics. So if you don't know what this is called the famous Mobius strip. Okay, so a Mobius strip is pretty straightforward. You could think of it as just a piece of paper like that portion, and you twist it and put them together. You get that. So here's a little twist of it itself. Okay. Now, the interesting part about this Mobius strip is the orientation. Okay. Now, what I mean by orientation is like if you're walking along, so let's say you start at P, and you look straight up as you walk along. So if you look straight up from here, you're looking inward, right? You're looking into the strip itself. And as you walk along, keep walking, you're still looking up, still looking up, still looking up, still looking up, so still looking inside. And eventually, as you walk, you actually twist. So instead of looking this way, you eventually look that way at some point. And now you're on the outside of the strip until you eventually get back to the strip and you go back inside. Okay. So that's actually very interesting when it comes to thermodynamics itself, is the vectors itself, or in this case, the vector fields of a Mobius strip goes into 2 spots, inner and outer. So what that tells us is we have an orientation depending on where you're at on the surface itself. Okay? Now, in our cases, we're not going to be talking about the Mobius strip because that breaks a lot of what we're doing. We're just going to do the fundamental stuff. So in our cases, our surfaces are going to have one orientation. Meaning, are you looking up or are you looking down? that's pretty much what we're going to be dealing with. Okay. So, or in this case, are you going to be looking towards the surface or away from the surface? Okay. So this comes into play here. So this is what we're going to be talking about itself. Okay. So we're going to do let n be a unit normal vector. Okay. So in that case, we're going to have two possible outcomes we're going to have. Okay. So we're going to have something called a positive orientation or a negative orientation. Okay. So a positive orientation looks like these two here. Okay. Where you're going away from the surface or going outward. So these two are called a positive orientation. And a negative orientation represents you going in, either into the surface or going down. This is called a negative. So as you notice, the reason why the Mobius Strip breaks on us because it has both a positive and a negative orientation at the same time, depending on where you're at. Here, however, it doesn't matter where you're at, you're always going to have one or the other. So gravity is an example of a negative orientation because gravity pulls you towards the insert, right? The inner portions. Right? Because you wouldn't have this, because if you jump, you'll be going to space, right? Because they want you to go out, right? The vector field wants to push you out, which is a big no-no, right? That's all. Okay. So we're only be talking about positive or negative, right? One or the other itself, okay? Which is kind of nice. And that's going to be our definition. Positive means goes out, negative means it goes in or goes down from the surface. Okay. Now that we have kind of that happening, let's apply this to vector fields. Now, the good thing is when it comes to apply to vector fields, it's the same thing. We're going to have a positive or a negative association or to it. Okay. Remember, this vector field is fluid, right? It's not just like straight surface now, it's the actual vector field, right? It's bending depending on what we're actually dealing with, right? If it's the flow stuff, or it's the gravitational pull, right? It's bending in its curves itself. Okay. So this is a very interesting topic because what we're going to do is we're going to look at this, look over this vector field and see the surface on top of it. Okay. So in other words, if I look straight at it here, like if I'm just on the x-axis and like straight across, I don't see what the y is, right? Because I only see, straight up and down. So I see a circle. And if you notice anywhere I go on any axis, if I look straight up and down, I see a circle. Okay? And that's what we're going to be doing. So we're going to do, so given a surface and a vector field, like we have here. And what we're going to do is we're going to look at it and we're going to project it to a two-dimensional plane. Now, in most cases, it's going to be X and Y, but it could technically be any ones we want. We could be in Z and Y or Z and X, right? Like I said, right, if I look here, I don't know what Y is, but I see flat, right? Like if you're looking at a door, if you look at a door, you can't really see the depths of the door. You just see a rectangle, right? Same thing applies here. It's a two-dimensional sphere that relates to a three-dimensional surface. Okay, so how do we put this into practice? So when it comes to our let's go, our equations. So given a vector field, okay, with a denoted orientation, meaning we know it's positive or negative, right? We know it's either going to be positive or negative from our vector field. And we also have a unit vector field, n, that we talked about, right? The normal vector field. Then our surface integral over the vector field, this is what this represents, a surface integral over the vector field is given by this equation here, which we've actually talked about this earlier already, right? But the good news is I can rewrite that in a way, okay? Now, because this is so popular, and we'll talk about that, why this is so popular, this is called the flux of F across S. That's what it's defined to be. And we'll talk about what it means by flux in a little bit. So it's actually fluid going through it. Okay. Now, an alternative defining the normal unit vector is again going back to our U and V, changing our parameterization, because we know a normal vector to two vectors is just a cross product. So essentially, it's just the vector field dot product with a cross product of the vectors of U and V in terms of the partial derivatives of U and the partial derivatives of V. Okay, now let's talk about what I mean by the flux. Okay, so what I mean by flux is this is saying is the rate at which flow is going through the surface. Given a vector field. And that is so interesting. That's why it's called the flux of the vector field across the surface, whatever our surface is. Hence the reason why flow, right? Flow represents a lot of stuff, water, believe it or not, electricity. And a lot of stuff actually goes in the same direction as water, which moves in a curvature. Hence the sine and cosine curves, right? Okay, so we have our new equation for the flux over a vector field, right? Not just over a function f. So let's do roughly the same equation we did last time here. So let's find the flux over this vector field. Again, across the sphere, x squared plus y squared plus z squared equals 1. Okay, so everybody's favorite, I know, right? Back to spherical, right? So in our case, x, y, and z, right? It's only going to be in terms of phi and theta. So it's literally the exact same equation, example we had earlier, right? X is just going to be, well, let me just do that. So rho is just going to be 1, right? Because the square root of 1 is just 1. So it's just going to be sine phi, I'll put this in vector format. Sine phi cosine theta, it's going to be the x. Y is going to be sine phi sine theta. And then our z is just going to be cosine phi, right? Okay. So this time, let's take the partial derivatives. Well, we did it last time. I'll just do it just for practice sake. So it's not too long. So partial derivative with respect to phi. So this is going to be positive cosine, and then cosine theta. Same thing. Cosine phi, sine theta. And then this one is going to be negative sine. Or actually, with respect to phi, right? Yeah, that's right. So sine phi. Then with respect to theta, so it's going to be negative sine, so negative 2 sines. respect to theta, so let's get cosine. And this one's going to be 0. Right? There's no cosine. There's no theta there, so it's just 0. Okay, so again, we did this last time. We're not doing the magnitude this time, we're just doing the cross product. And, after doing some work, you eventually get this. Right. So we're actually almost done. Right. So we had to do this, so we got that times F. Now, when it comes to times F, we got to find our vector field at our parameterization. Okay. So that just means you're just plugging in Z, Y, and 2X for each individual case, right? So in this case, it's going to be Z. So just cosine by Y, which is this one. And then 2 times this. Okay. And then finally, notice it's just a setup, right? This is the worst part. We're going to do the dot product. Right, so remember that means it's going to be, where is it? Oh, this is my vector, right? So this times this plus that times that plus that times that. Right, so after multiplying each one, just notice I just write down and adding everything together, you get this. That's a lot, right? Okay, now let's integrate this bad boy. Oh, right, since it's a sphere, right? So it still goes from 0 to pi and 0 to pi. That's the nice thing as a sphere. We use a uniform. So this goes right here. Oh, I missed the cosine. Right. There we go. Okay. Isn't that lovely? However, there's got to be a nice way to do this. Well, because there's a plus, and because we know rules of integration, that means I could do this plus integral of that, right? Remember, we could break up the integrals with plus and minuses, do each one individually. And let's just do that and see what works out, okay? So I'm just going to ignore this for now. I know it's there, but I'm just going to ignore it. And I'm just going to do this first, right here, right there. Okay. So if I just do that, and again, remember it's multiplication, and these are bounded by just single numbers. So I could break this integral by multiplying, meaning this becomes the double integral of just the phi times the double integral, or sorry, no, what am I doing? Just single integral of cosine theta. Right, we did this in the last question. Okay. Now, the reason why I want to do this is, well, what's the integral of cosine theta? Negative sine theta, evaluated at 2 pi and 0. Well, if I plug in 2 pi, I get 0. And if I plug in 0, I get 0. What's 0 minus 0? 0. So now I have a question for you guys. If this integral is 0, do I really need to evaluate that? What do you guys think? No, because 0 times anything is 0. Aha, told you, there's shortcuts everywhere, right? Little cheat sheet there to do it. So all this integration, all that hard work would end up being 0. So that's gone. So really, it does my work in half. Hence the reason why, knowing integration properties really does matter when it comes to these horrible integrals, right? Especially when it comes to sines and cosines. So really, all I'm doing, this is all gone, is a double integral from 0 to 2 pi, 0 to pi, of just that. Oh, still horrible, but not as bad as this anymore, right? Now again, notice we actually did this already, where I'm going to break up this integral from 0 to pi of sine cubed phi phi times the integral from 0 to 2 pi of sine theta squared, right? So notice we already did this integral. The only difference is I think last time it was cosine instead of sine. So hopefully I can skip this step, right? This is going to be theta over 2 minus 1/4 sine 2 theta. And again, this is going to be the same property. Break it up. So I actually have it here, don't I? Where is it? Here it is. So essentially is the same thing we just did earlier. Right? So it ends up being this, evaluate at 0 and pi. So it's the exact same integral there. So this ends up being this integral right here. Okay. And then this one is just be the 1 minus of itself. So essentially, believe it or not, wow, look at that. You get the same answer. Well, kind of makes sense because I actually got, that's the vector field of x squared. Well, how ironic how that works. Huh? So this is the actual vector field of it. Now, what does this mean, right? We just talked about flow, okay? So what this is saying is this represents the rate of flow through the sphere. Hence why it's called the flux of the vector field. Now, we have not talked about how to find the flux of a vector field if a parameterization is just x, y, and z. Okay, that's what we're going to talk about right now. So this is our equation or our integral in terms of x, y, and z. Okay. So again, just in case you forgot, right, f is in terms of pi, qj, and rk, right? Those are where that p, q, and r represent. Okay. So it's the double integral of the region from x and y. This time, however, it's going to be p times g, or in this case, like z of x. And this is the partial derivative with respect to y of the g function, or there's just the z itself. Okay. All right. Like everything, well, what if everything's in terms of that now? So let's try. So find the flux of f, where our vector field is in terms of the z, y, and oh, yeah, look at that, the same one. Well, let's find out what's easier to use, right? Where S is bounded by the solid enclosed by 1 is equal to, do I want that? Yeah, 1 is equal to z plus x squared plus y squared, and z is equal to 0. So same vector field. Now this is a little different, right? This is not our sphere, right? So it's going to look a little different when it comes to our answer. Okay. Now, remember, you can use a trivial one, x, y, and z, if you can solve for one variable very simply. And notice we can't, right? We can solve for z much, much easier by just bringing everything over. So we'll get z is equal to 1 minus all of this, which is great. So that we can use the trivial one. Okay. So in terms of our equation, this is our g function, right? That represents our g function in the equation. Okay. So what that means is I need to find a couple things. I need to find partial derivative with respect to x and the partial derivative with respect to y first. So partial derivative with respect to x and partial derivative with respect to y. All right, good. We're halfway there in our equation, right? Okay, next step is we need to find p, q, and r. Now, we need to find p, q, and r with respect to only x and y. That's the key thing, right? Because this has a z here. So technically, if I plug everything in, this is just going to be 1 minus x squared plus y squared I, then yj, and then 2xk. Okay? So that means this is going to be my p, this is my q, and this is my r, respectively. Right? So therefore, now we can write our double integral over a region. We'll talk about x and y right now, with our bounds, but we'll just talk about our equation. So let me put my equation up here. All right, so it's going to be minus p times dg dx, so this one here, minus q, which is y, times this with respect to y, plus r, like that. So that's how we set it up. Okay. So I'm not going to multiply stuff yet. You probably know what I'm about to do. But I'm going to simplify some negatives everywhere, make it a little easier to look at. Okay. Negative and negative make a positive. So it's going to be 2x times all of this. Negative and negative make a positive. And we get that. Again, just easier to look at, right? That's all. Okay. Well, x squared plus y squared. Gotta go to polar. So r and theta. So if I plug it into here, well, actually here, so z is 0, so therefore r is going to be bounded between 0 and 1, because r squared equals 1, so r is equal to 1. And theta goes from 0 to 2 pi because we have a circle, right? X plus y squared is a circle, so it goes the entire length of the circle. Okay, so now if we plug this everywhere, don't worry, you actually will like this integration. There's no craziness here. Not that bad. It's just lots of fractions everywhere, right? So plug in everything we know. This ends up to being r squared, which is nice. So it's going to be the integral, or the double integral of 2 times cosine. Okay. Now, remember, when it comes to, when we convert to polar, you multiply it by r, right? So what I'm going to do is I'm going to already multiply by r. So for example, instead of 2x, it's going to be r squared cosine theta, right? Because I already multiplied every term. So each term has to be multiplied by r because it's a distributive property. And here it's going to be 1 minus r squared, right? Because it's r squared. Plus, so this is squared. So if I multiply by another r, that gives me cubed. Plus 2 again, times this, times another r, so r squared. All right, so before I go any further, that makes sense, everybody. Me doing that. Is everybody comfortable what I just did? So everybody good? No confusion? Okay. I'm assuming that's it. Everybody say yes. Yes. Okay. Okay. All right. So next step, I'm just going to distribute this to here. So I'll just put it underneath. Right. This times 1 minus, all that happens is going to be r to the 4th now. Right there. And then plus everything else. Right. That's all it is. Everybody see that? It's a little light. Hopefully you guys can see that. Okay. So now I'm going to take the integral of r. Okay, here. Integral would be r to the 3rd cosine theta. Integral here, r to the 5th cosine theta. Integral here, the r to the 4th. Okay. Integral here, r to the 3rd. Evaluate at 0 and 1. Now, the best part is when you plug in 0, everything's gone, right? So you're just subtracting 0. And notice if you plug in 1 and 4, all we're going to do is just get fractions, and everything's in terms of theta. Oh, this is a square. This is a square. Yeah, r squared. There we go. That's the only square we have. Okay. So that means I can add this, and that together. Can we see that? So adding these two gives me 4/3, and then subtracting 2/5 to it, I get 14/15 cosine. So 14/15 cosine theta plus 1/2 sine squared theta. E theta. So notice this actually is not bad. You know, the setup was the difficult part. Integral of cosine, positive sign. So 14/15 plus, we've been doing this so many times, right? Probably memorized it already. All evaluated at 2 pi and 0. And we're actually done because I plug in 2 pi, 0. Plug in 2 pi, this becomes pi. Plug in 2 pi, gives you 0. Plug in 0, that gives me 0. Plug in 0, that's 0. Plug in 0, that's 0. That's even nicer. So all that's gone. So literally just get pi over 2. Now, this is technically our answer, and I'll show you why technically this is our answer. Because the flux of a vector field can be very confusing. Now, what I mean by that is, like we had earlier of the Mobius strip, where you have both inward and outward, right? Both negative and positive orientation. We can also have that same thing happening to vector fields here. Okay. Now, I wouldn't expect you to do this. It's just a simple example of how this will apply. But if we would actually graph this out, so graph this vector field and the surface all in one, we get something like this happening. So here's our roughly surface applied to our vector field. Okay, so that's kind of like our surface. I know it's kind of bad. So it just goes around. Yeah. So the first part of our vector field goes up if you're on the surface, the top of the surface, which is fine, right? It's a positive orientation. We'll call that S1, surface 1. However, if you're on the bottom of the surface, meaning you're literally walking along the bottom, right? Like if you look up, you're going down, it shoots this way. So if you're right here looking up, you're looking this direction. So it actually has two orientations. Okay. So whenever you have two orientations of a vector field, the entire flux is equal to the sum of both of them put together. Now you may be saying, you got to be kidding me. We got to do another integral to this. Yes, but just wait. Now, because it's negative and positive, right? This is positive, so therefore this is negative. Well, in terms of z, because we have everything in terms of x and y, z going up here is positive. So therefore the negative will just be negative z of what we have. Now the great thing is, if we go back up here, we are told z equals 0. Right? That's what we're told. Z equals 0. So if I go down here, that implies the vector field going down here is negative 0 or just 0. So now we're going to take the double integral of 0 dA. Now, anybody know what the integral of 0 is, just in general? Trick question. Zero. Because if you take the integral of, let's say 0 dx, for instance, what does that say? 0 times x plus the constant. Oh yeah, you put the constant, right? Yeah. But we have bounds, right? We actually have bounds in self. So that's from A to B itself. So this is bounded from A to B. Well, what's 0 times x? Can you plug in your constants? No, it's just 0. Don't you love it? So this integral or this flux going down is just zero. So technically it's pi over 2 plus 0, which still gives you pi over 2. Again, I want to expect you guys to do this, but it's just a fun little showing you guys when it breaks, how we could still apply it to our fluxes. And this is actually an application of, when it's actually done, because some people go this way, that way, and